Before I start, can I just read out our diversity statement? Participants are reminded to be mindful of inclusion and accessibility throughout this meeting and to endeavour where possible to promote diversity in its widest sense. I'm Bill McDonald, I'm the CEO of ScotCHEM, and it's my pleasure today to introduce Paul O'Brien, Cluster Manager of DeepWind Offshore Wind Cluster and Senior Development Manager with Highlands and Islands Enterprise. And your talk today, Paul, is the new alchemy, power to X. And over to you.
Hi everyone, good afternoon. Right, so I'll be talking about what's actually happening in the offshore wind sector, and we're looking specifically at using large-scale offshore wind to produce initially hydrogen, but we're talking about the new alchemy, as I'm calling it, and you'll see in the introduction why I'm actually referring to that. Okay, so we'll do the introduction, we'll cover the future scale of the offshore wind market, then the offshore wind's alternative markets and what's driving the look at different, instead of just producing to the grid, we'll also be looking at what are the market drivers for looking at things like hydrogen and hydrogen at scale, and then a forward look to what it will look like in 2050 if everything is going to go in the direction that we're heading in at the moment, what that will look like in 2050. So why am I talking about alchemy? So if we go back in history, the early sort of ancient Greeks believed that everything was made of just the four classic elements: earth, water, air, fire. And then Aristotle came along and he added a fifth, which was ether. And later in the rise of sort of the alchemists, particularly in the 8th century in the Arabian area, we have sulfur, mercury, and salt to become the 8 basic elements. And they believed at that time that they could take those 8 basic elements and that everything was made up of those. And if you knew the right catalyst or elixir, that you could transform them into any other element or substance. So remember that, and we'll get back to that later. The cluster I represent, the DeepWind Offshore Wind Supply Chain Cluster, which is a Scottish cluster, of course, and it's pretty big. We're currently just approaching the 450 mark. We've got quite a diverse makeup in the cluster, but very, very strong in the upper echelons of the wind industry, with 22 offshore wind developers, a turbine manufacturer, which is MHI Vestas. We have 12 tier 1 companies, so the initial contracting companies that the developers tend to deal with directly for very large contract packages. We've got local government, 6 councils, universities, and 4 colleges is also involved. 25 ports, 3 of the other associations in Scotland with AREG, DECOM North Sea, and Subsea UK. And that leaves us 371 of the supply chain companies, which extend right across the scale from multinationals right down to micro SMEs. This is the largest cluster, offshore wind supply chain cluster in the UK, and it is the UK's leading cluster for floating wind. These are just this is a quick snapshot of the actual developers that are involved. There's 22 of them on that screen, and there's some household names in amongst it. There's some oil and gas players. We've got 4 super majors, major utility companies from across Europe and beyond, along with some independents as well, who are all looking at developing offshore wind either in the UK or Scotland in the future as well. We are also engaging with our academic partners which are in the cluster, And there's a number of areas that we've begun to look at. A lot of it's quite early stage, but that's a list of some of the things that we're looking at with those partners. I'll point to the life extension, recycling, repowering joint industry project, which is not yet kicked off. We're a DeepWind supply chain cluster as an associate member, but it also involves two of our university members, Robert Gordon and Strathclyde, working with the catapult. And I'll draw your attention to UHI, University of Highlands and Islands. One of the things that we're going to be looking at in the future is seaweed farming and the opportunity to co-locate that with offshore wind to use the very large scale areas of sea which winds takes up. And we're thinking that that would lead itself to co-location to do very large scale seaweed farms, and then what follows on for them. And I'll return to that later. So research-wise, DeepWind's engagement with the Floating Offshore Wind Centre of Excellence. We've also been working with them already in a couple of areas, and we are a stakeholder of the Centre of Excellence. So the areas that we're looking at with them, the floating substructures, how to fabricate them in Scotland, looking at the mapping of the floating offshore wind supply chain, and we've got a great deal of the members that are that supply chain already in the cluster. We have a subgroup for floating offshore wind. Other areas, I mentioned the aquaculture crossover, potentially with floating wind. That will potentially come out more when we get to ScotWind, and more of that in a minute. And we're also looking at, with the Oil and Gas Technology Centre and the Catapult, we're also assisting them with looking at powering offshore oil and gas assets with floating offshore wind. So that's 4 of the areas that we're looking at in this space. So just a bit about the scale. We're talking about very large scale production of green chemicals, so that requires a lot of electricity. And you can see there that we are well on our way to delivering almost 10 gigawatts of offshore wind just in Scotland. And that's a breakdown of where we are. We've got the operational in red there. We have got the under construction in orange. The yellow is consented, and some of them are moving into the construction phase at the moment. And then we have 2 large projects from SSE Renewables, which are yet to pass through Scottish Government's consenting system, but their 2 projects alone are over 4,000 megawatts. So very, very large scale projects. Some of the largest projects in the world are coming down the line in Scotland. Now, we're not resting on our laurels there. Scottish Government have got plans for a further round, and I'm just going to run through that. There are 17 sites, but they have been broken down into 3 types of these sites, depending on what needs to happen to them before they can be made available to the offshore wind industry, or after what kind of work is required. So these sites, the draft plan options, DPO sites as they're called, so 2 of them there on the East Coast, E1, E2, they're already signalling, so Crown Estate Scotland and Marine Scotland are signalling that these sites will require further levels of survey and assessment. In a similar vein, the green sites, 6 of them, are looking for further ornithological constraints, so there will be more concentrated effort in looking at the effect on the bird populations in these areas. And then finally, we have the last of the 17 sites, the blue, and you can see that for the first time we're breaking away from these concentrations where offshore wind is being built at the moment in the Firth of Forth and the Moray Firth. So we're now looking to develop offshore wind in areas where admittedly the grid is a lot weaker on the west coast, in the Northern Isles, right up there in Shetland as well. And these sites are bringing the benefit of offshore wind. The money that's spent on the offshore wind is going to run into the billions, and we're looking to see some of that sort of find its way into the communities that are very close to these sites on the west coast in particular, and in the Western Isles and Sutherland and Caithness areas. So we're looking for transformational activity in these areas if all of these sites move forward. And we don't know yet that that will happen, but we'll find out very shortly how many of the 17 will go forward. And this is a further 8 to 10 gigawatts on top of that 9.4 that I showed earlier. So we're looking at roughly, could be round about 20 gigawatts. That's a lot of electricity to get onto the grid, and particularly in the north of Scotland, where we have some issues. And that leaves us with a market. So looking at Scotland, but the rest of the UK, if you take the whole market, this is a breakdown by operational, under construction, ones that have been consented through the planning regime, and others that are in the pipeline. UK has a target of about 40 gigawatts by 2030, which is highly ambitious. But you can see from those numbers there, if everything that's in the pipeline was consented and built in the time frame, we are round about the number. And it would only take 1 or 2 projects from the new rounds, so that's the ScotWind round in Scotland and round 4 in the UK, for us to reach that magic 40 gigawatt target number. So it's highly achievable now. It looked very difficult when it was first announced, but it's now looking potentially achievable with maybe some space to spare. Now, I mentioned in the north of Scotland, we're looking at some weaker grid areas, and that means expensive grid upgrades, which are partly borne by the developers themselves. It's likely that constraint could be an issue on the west coast and the Northern Isles, as it has to make its way right down the whole of the UK down into the south, where the levels of demand are the highest. And 2 things happen there. One, the companies, when they are constrained by national grid, when there's too much wind on the system, because they're the deal that they get from national grid, they are paid when they're told not to produce. Now that means there's an opportunity for them to add that to any existing hydrogen production, and effectively providing the rules are that national grid say that providing they do not put that electricity back onto the grid in any shape or form, they can turn it into hydrogen that could be used in transport, can be used in chemicals. As long as it never finds its way onto the grid, then that contract is still valid. So they effectively get almost free electricity when they're constrained, which could lower some of the cost of producing that hydrogen. But they need to invest in the rest of the hydrogen infrastructure to make that happen. But it's a factor. We also have the highest transmission network user system charges in the UK in the north of Scotland. And these are much higher than anywhere else, particularly right down the south, where the levels of demand are high. And it's a sort of measure of how far the electricity would need to travel to get to those centres of demand. So those high transmission charges, the weak grid and the expensive grid upgrades, all are leading to think about using something else, hence why we're talking power to X, something else besides electricity and how to take it to the market. So the diagram is from Siemens Research and Dr. Ian Wilkinson, who worked with previously. And what it basically shows is that turning it into the electricity into chemicals such as methane, hydrogen, ammonia is probably the best way to store electricity at very large scale. It's almost certainly the the longest of the bubbles there, from 100 kilowatts right up to thousands of megawatts, and it's for the longest storage time. So that's very important when you're looking at alternative market drivers. Recently, in fact, just last week, the Offshore Wind Energy Council published this document, Offshore Wind and Hydrogen. And for the first time, we are really starting to talk about the scale required to deliver this green hydrogen future. It's a huge market, or potential market, with the hydrogen demand somewhere, depending on which report you read, by 2050, it could be 100 to 300 terawatt hours, and it could deliver 320 billion of additional GVA between now and 2050, plus 120,000 jobs. So there's a number of things linked to this that have to happen before we get anywhere near some of those numbers. The technology acceleration, we need to get the cost down, particularly of electrolysis. And you can see there in the cost reduction, they believe that in the next 10 years, we could see a 58% cost reduction in the production of hydrogen on the electrolyzer side. This is for PEM electrolyzers. It also says there that Julia King, who's Baroness Brown of Cambridge and is the offshore wind sector champion, she's calling for rather urgent action. So within the next 5 years, she's saying it's critical to achieve this cost reduction if we are going to compete in what is now heading towards certainly a European, if not global market in the production of green hydrogen. Now here's some of in the same document, it shows some of the innovation challenges. And you'll see down the side there, a lot of it's related to the chemistry of the electrolyzers, the membranes that make it up, the cells, the anodes, the cathodes, etc. And there's some cross-cutting themes, standardization testing, data sharing, etc. I'll not run through the whole thing. Some of these time to market figures might look a bit long, but I'm not sure it takes into account what's actually happening in the universities at the minute. Some of this stuff has already been widely looked at by the universities for some time. So we might not have to wait some of the length of time, 8 to 10 years in the case of the advanced membrane materials. It's been looked at for the last 5 years or more, and we should get to it quicker than that, but time will tell. So if we've got the hydrogen and it's at the wind farms, which I've shown the location of, how do you get that hydrogen to the market? Currently, pipelines, you need to get to a particular scale for pipelines to come into play. So we're looking at some form of transfer of potentially liquid. Hydrogen is, in its gaseous form, is very difficult to store and deliver. A very expensive way to try and move hydrogen about as a gas, unless you've got the pipeline. So there is a number of areas being looked at. Cryogenic, and that's Kawasaki's first ever liquid H2 carrier, which is cryogenic. Susio Frontier, Susio is Japanese for hydrogen. The liquid organic carriers, LOHC, they're looking at a number of potential candidates for this. And this is involving a catalytic hydrogenation, dehydrogenation cycle. And a number of the candidates are shown there: toluene, dibenzyl toluene, N-ethyl carbazole. There's a few others as well there. And basically these liquids are charged with hydrogen and turn into another compound. Toluene is methyl cyclohexane, and dibenzyl toluene becomes perhydro dibenzyl toluene. Get the chemistry right in a minute. One of the big options that everybody's really jumping on is turning it into ammonia. So with nitrogen capture and then a synthesis step using a very old process, Haber-Bosch. And then green methanol, providing you have a source of CO2. And Scotland has certainly a number of areas where we've got CO2 available. And there's also a lot of work going on in looking at both of those, green ammonia, green methanol, looking at new electrochemical developments, synthesizing these, which could change the game again from some of the very old methods that are still deployed. Then, once we've grown the market to a point where we've got very large scale of hydrogen production, then pipelines come into the equation. And we could also mix it in with natural gas. But one of the things with that is that we would, I think, then need a way of actually separating that out when it arrives at its destination. So you could use the gas grid, existing gas grid, for storage of hydrogen, but also transport of the hydrogen gas mixed with natural gas. Now, at least up to about 20%, which is the number that's been looked at in the UK at the moment, and has already been looked at within countries like Germany, etc. So that's important, but it leads us to another question about, as we're saying there, there's other green hydrogen related chemistry, separation systems. If we're going to put the H2 into natural gas, how do we get it back out? And there are a number of projects. There's particularly an EU project on the go at the moment, and that, in fact, is coming to an end in this year. It's called Hygrid and involves Dutch and Spanish companies, along with at least one Swiss company, looking at a three-step process using membranes, electrochemical hydrogen is also being looked at, and depending on how much of the hydrogen is in there would depend on the steps, and temperature swing absorption is also there to just remove the humidity that is still there from the previous steps. So this hybrid process is looking at extracting the hydrogen from the natural gas flow, and this is quite important if you want to use that hydrogen. If you want to transport it for the gas pipeline, you want to recover it for use in transport or as a chemical feedstock. We need clever ways of separating it out from the natural gas. Other areas I've mentioned, ammonia. It's looking very, very popular, particularly in Japan at the minute. But again, the question is, do you use the ammonia as a feedstock, or do you crack it and recover the hydrogen? So again, another area where we've got to get very good at extracting hydrogen from the ammonia if we intend to use it for the uses shown there, particularly fuel cell vehicles or as a feedstock. Ammonia itself can go into the fertilizer industry and potentially with gas turbine power generation as well. But if we want to recover the hydrogen, we again have to have a really good way of cracking the ammonia with a very high purity of hydrogen coming out of that. Ionic liquid compressors, they would be looking to replace the type of compressor that's used at the minute. They're a lot more efficient, particularly with hydrogen, and we could see a big rise in the type of ionic liquids required. So the manufacturing of these is going to be a big area in chemical manufacturing in the future, probably not too distant future. And one of the other areas that we're looking at the minute with Zero Waste Scotland and other players in the joint industry project, which is looking at potentially recycling of the composites and carbon fiber which are in the blades. There's some numbers there about basically not putting this to landfill. There's just, for a start, there's just too much of it. We are heading towards, you see 24,000 tons a gigawatt. I showed earlier that the UK's already got a pipeline of about 57 gigawatts on the cards, and that's just over 1 million tons of, unless we can come up with a way of recycling these composites or manufacture them in a different way so that they're easier to recycle, we're creating ourselves a big landfill problem if we can't sort this out. And it's the chemistry, it's down at the chemistry side of it that's going to solve this problem. Meanwhile, in Europe, the European Commission has announced a really ambitious clean hydrogen approach, a strategy looking at ramping up, first of all, electrolyzer capacity, 6 gigawatts within the next 4 years, rising to 40 by 2030. Now these are, if you're not familiar with the electrolyzer, we're building 1 megawatt, 5 megawatt, 10. I think the biggest project being talked about at the minute is about 100. So these numbers are enormous compared to where we're at the moment. And it's going to take, for that 40 gigawatts, 10 million tons of hydrogen, we're talking 80 to 120 gigawatts of renewables, mostly wind and solar, to be in place by 2030 to deliver just hydrogen. Nothing to do with the electrical side or onto the grid. This is just to produce the hydrogen. But they've got they're proposing a carbon contract for difference, which would be a big market driver across Europe. And what we're trying to find out at the minute is, can the UK, given that we are leaving, can we still tap into this in some fashion? And that discussion is ongoing at the minute, because this will be an important market driver for green hydrogen across Scotland and the UK. And again, the stationary grid scale and feedstock, the hydrogen we mentioned, ammonia and methanol, these are very important elements and chemicals for this end use of the hydrogen. So if we've got a hell of a lot of hydrogen in the North Sea being produced, say, by Scotland and the rest of the UK, how do we get it into the other markets in Europe? Because we don't just want to produce enough for ourselves, we want to export as much of this as possible, because a bit like oil and gas, the opportunity is there for a complete export market, just because of the scale that Scotland in particular can deliver offshore wind. It has one of the largest economic zones in Europe offshore. So the amount of wind that it can deliver is the equivalent of most of Northern Europe. So it's huge. So if we want to tap this, we'll need to look at an export market. And the question in this map, this is the proposed hydrogen backbone, which is involving 10 of the national transmission system operators that run the gas grids across those countries. They're talking about transforming it into a hydrogen grid. So how do we connect into that? Well, luckily enough, the oil and gas industry, or the gas industry in particular, has done us a bit of a favor there by building infrastructure which already connects in to France, Belgium, and Germany. And it covers quite a bit of the North Sea between Scotland and Norway, and right into the north of Norway. And certainly on the Scottish side of it, you can see that dotted line off the coast of Scotland. That is part of our exclusive economic zone that I mentioned. We can produce a hell of a lot of offshore wind to hydrogen there. And eventually what we will be doing is feeding that into that those pipelines, that as natural gas dies down, we can add hydrogen at a percentage, providing we can recover it. So that's why that's very important. But you can see there that we're talking about a very large amount of offshore wind, 200 gigawatts. The report last week spoke about 240 gigawatts. So we're in that sort of round number space to produce about 80 gigawatts of electrolyzer plant. That's huge amounts of hydrogen. And if we do that, then we can green the UK grid, and we can also help Europe also do the same. So if we do all of this and it all works well, what does the industry look like 2050? So we're talking about green chemicals. So hydrogen is really the first step. And something else that we need to do, we need to be able to use seawater to produce the hydrogen. So electrolyzer or methodology has to be found that can utilize, instead of fresh water, utilize seawater, because it's more abundant than fresh water. And in some parts of the world, fresh water is an issue, not feedstock. People need water more than this process does. So if we can use seawater, it opens up a huge industry across the whole of the globe, anybody that's got a coast. So offshore wind, seawater, and again, I'll refer back to what I was talking about right at the start, the alchemy, the 8 elements. So we're using air and water to produce what you could consider the base of a complete chemicals industry. We're going to transform 2 of the common components globally, and we're going to produce other elements from it. So that's where the alchemy comes in. So if you've got hydrogen, we then look at producing nitrogen, and from that we can manufacture ammonia, and that can be used in transport. In fact, they're all there. If we crack it at the end, we can also put it back into the gas grid. Providing we can get the purity up, we could also put it into transport as well. But storage and feedstock could come from cracking the ammonia once it's reached its destination. How to transport that is usually bulk carrier, a bit like the LNG market. I think it's going to be very similar to that. I mentioned right at the start co-location, aquaculture and seaweed. So that opens an opportunity to very large scale harvesting of seaweed, putting it through the biorefinery, and then getting a number of products which seaweed already is involved in that market: additives, pharmaceuticals, cosmetics, nutrients. If we then look at what we could do if we've got green hydrogen and CO2 capture, which I mentioned earlier for methanol production, there are a number of other things you can do with it. And if you move into longer and longer hydrocarbon chains, you can duplicate the type of chemistry involved in petrochemicals. But ultimately, what we need to do is move away from CO2 capture and move to direct air capture of the CO2. And then we'll be taking CO2 out of the air and reducing the volume of it, which is what we really need to do if we're going to tackle climate change. Now, that's a nice way of looking at what this is going to look like in the future. But one of the questions that comes up all the time is, what about all of that oxygen that's been produced at the electrolyzer plant? So you've got hydrogen, but there's a hell of a lot of oxygen. Can we not do something with that? Well, you can. Glass, gas to liquids, metals oxidation, these processes use oxygen, particularly in the oxyburners, to lower their energy consumption and to lower their NOx emissions. And that's a very good use of the oxygen. But ultimately, we want to get to the point where these also transition to green fuels so that we don't need to do that. But oxygen is probably still going to be required at that point to assist with the overall burning. So that's a picture of what basically an offshore wind to hydrogen future, what it enables. And it covers a lot of the chemical industry at the minute. Now, if we can deliver that, we will have reduced emissions by a huge amount, and we'll be tackling, particularly with the CO2 capture, climate change directly. So thanks for your attention, and that's me. And we're going to switch over to any of your questions. If you've been using the chat, we can now take some of the questions. I'll be happy to try and answer them.
Okay, we have a question here from Ian Hill. The vision of a green chemical industry 2050 is very impressive, but how will you mitigate against the fragmented location of many of these activities? In other words, will it be hard to achieve because the components are in different places?
Right, well, of course, we're going to have to produce it in one place because at the moment, the rules, particularly the European rules on what is green hydrogen, means that the electrolyzer plant at scale has to be actually directly connected to offshore wind. And that's the same whether it's solar or onshore wind. The rules in Europe at the moment, for it to be classed as green, it needs a direct connection. Now, offshore wind is going to be on the coast, of course, and further off the coast. So most of this will be related to coastal sites. A lot of the ports on coastal sites already have a number of these industries actually in the port. For steel manufacturing, they're usually very close to a port for export of that steel, also to bring iron ore, etc. in. So where possible, the co-location of other industries in these ports is very important. Now, as we get into more, if you take the west coast of Scotland, yes, we're going to have to transport, take Western Isles. So Stornoway Port would be an obvious place for the hydrogen facility to be. So the storage there, depending on how we move it, initially it's going to be by bulk ship carrier. So a port is an obvious choice. They go in there, they load it up, and they take it to the market. And that's exactly what happens in LNG market. So it comes from wherever natural gas is available across the world, and they transport it cryogenically by ship. And in fact, the UK brings in about 60% of its natural gas as LNG at the moment. Two large terminals, one in the east, one on the west coast down south in England and in Wales. And that's just a common way of transferring it. And hydrogen, depending on how we carry it, is going to be very, very similar. So although renewables tend to be in remote areas or further offshore, the infrastructure is actually available to deliver it into those markets around the world.
Okay, we've got another question in from Bill McDonald. Lots of chemical challenges are outlined in your talk. What would you consider be the critical ones to focus on?
Besides the reduction, I think the reduction of the cost in electrolyzers, it's going to happen, it's going to come anyway. So I think the ones that we need to concentrate on, if we're really going to see this industry move into a different place, is using seawater directly in the electrolysis. That would be a complete game changer. It could mean that we could actually deliver this offshore. If the wind farms, which are huge areas to cover, if we actually put the electrolyzers offshore beside the wind farm, we could load the ships up directly from it. We could also utilize offshore storage and geological storage, whether it be aquifers offshore, which we've got a number of in the North Sea. They'll be looked at for CO2 storage at the moment, but we could take it a step further and look at hydrogen storage there, or conversion into many of the other forms that we could transport as a liquid. So the key, the two areas, one is that it's the actual seawater being able to be utilized in electrolysis, and I mean without the step of the desalination, which incurs a lot more energy. We want to try and use seawater directly. If we cracked that, that would be a real bonus for the whole, not just the industry here, but globally.
Okay, the next question is, you mentioned possible European Green H2 CFD. Do you see a similar possible UK CFD?
Well, it would be great. The UK has led the actual development of contract for difference in offshore wind, and that's for electricity. And it has brought enormous cost reduction in the time that it's been introduced. Within the last 3 years, the cost of offshore wind has dropped from what was £120 a megawatt hour to the last contract for difference auction. It was down just below £40. So it's now less than the wholesale cost of electricity in the UK. The report that was out last week from the Offshore Wind Industry Council pointed to this fact, and they felt that they could achieve similar cost reductions in electrolyzers, and hence why this big jump that's shown a 58% drop from where we're at the moment to about 2030. So that kind of reduction is going to enable this market. It's up to the UK government. They have led in the use of contract for difference, so it would hopefully be an obvious step for them to introduce this as a way of enabling a hydrogen market in the UK. And it would be great if they did introduce it. As I say, the report is only out last week. The Offshore Wind Industry Council is made up of industry and government. BES is involved. So hopefully it's a signal that this is something that's been considered seriously by the UK government.
Okay, the next one. Where are the best examples in the EU or elsewhere in the world of this shift towards a truly integrated hydrogen economy?
And there's nothing really of the kind of scale that we're talking about at the moment, but there are a number of projects on the cards. We have green steel, which is really finding its feet in Europe at the moment, in Northern Europe. And there are a number of green steel projects where they are using hydrogen to actually smelt the ore. And that's why they're calling it green steel. Shell, in fact, announced a huge offshore wind to hydrogen project in the Netherlands. And it's talking about up to about 10 gigawatts of offshore wind. But the timescale for it is up to 2040. Quite honestly, I think we're going to get there a lot quicker than that. I think projects of that scale will probably be upon us within the next 10 years. There are literally, I've lost count of how many hydrogen projects there are across Europe now. Literally, there must be hundreds. They're all at different scales, but some of them are very ambitious, particularly in the Netherlands, now in Germany, and in other countries. Belgium is also looking at this. So what we need to ensure is that we don't lag behind, that we don't fall behind. Otherwise, a bit like offshore wind, we will be buying in the technology that sits on top of the tower from the Germans, the Danes, and the Spanish. There's an opportunity here for the UK to lead on this. So we can't be caught napping. So we really need to move quickly. And hence why Baroness Brown was really urging a 5-year call to action that would see us catch up, because I think we are going to have to play catch up with particularly the Netherlands and Germany, who are tending to lead the field at the moment.
Okay, the next one is, how can we drive net zero into the supply chain whilst also achieving significant reduction in low carbon emissions?
Well, it's, of course, it's a subject very close to my heart. us being a supply chain organization, the wind industry sees itself as leading the charge almost for climate change, because by decarbonizing the electricity market, and the UK is looking at something like 75 gigawatts. The Committee on Climate Change came out with that number last year, saying that we needed to reach round about that to decarbonize the electricity system in the UK. But over and above that, if we're going to decarbonize transport, industry, and particularly heat's a real challenge, and nobody's quite got the measure of that yet. Hydrogen and green hydrogen is one of the tools, and it's quite a large tool in the bag to help decarbonize those very hard to reach. The supply chain need to come up with methodologies that lower the cost further so that we can accelerate the market quicker. So now what we're trying to do with our Power to X subgroup that we've started up is to marry the two industries together. So the supply chain from offshore wind and the supply chain from hydrogen production working together to look at how they can integrate the two technologies to reach the kind of scale that's required to deliver this industry. So the supply chain really has to come to the party with innovation, collaborative innovation, particularly utilizing the expertise from the universities to take what is possibly close to market research and deliver practical solutions that will actually drive the cost down. And that's what we now need to do in this 5 to 10 year period.
Okay, do you see wind at this scale being greater than the Scottish coastline? Can you see further opportunities to collaborate with partners across the UK and beyond, or is the space too competitive and IP needs protecting?
Well, collaboration is actually the name of the game. Although we have enormous resource here, we are never going to match that demand. So Scotland, with just 5.25 million people in it, is not going to use up the kind of hydrogen that we're talking about. We have an offshore wind resource with 25% of Europe's resource across Scottish waters. It is enormous. We perhaps don't quite understand how huge that scale could be. The Scottish coastline extends out quite some distance. Initially, we will be relatively close to shore. Some of the projects at the moment are planned in the UK are out to about 100 kilometres. In the future, we'll probably have to go further than that, and we will still be in Scottish waters, even if we go out to, particularly in the west coast, 200 kilometres. We will still be in the Scottish EEZ at that distance, the exclusive economic zone. So we have a huge resource, and it will be a long time before we're anywhere near the saturation numbers that Scotland is capable of delivering. It's got a resource estimate from the offshore wind catapult of 625 gigawatts. That would take a very, very long time to build, way beyond 2050, more like 2100 or beyond that. So offshore wind in Scotland is going to be a huge industry for a very long time, and we will probably switch in this decade from just producing electricity to producing green hydrogen. And beyond this decade, we'll probably be producing more green hydrogen than electricity. And eventually it will dwarf the electricity production and it will take over the offshore wind industry, as that's what you do with offshore wind.
Okay, I think this is probably the last question. Do you think that there is an argument for kicking off supply and demand in Scotland in the near term by building demonstrator green hydrogen projects powered by onshore wind?
Right. We have looked at this already, in fact. The difficulty is that the onshore wind that we've got at the moment is not of the kind of scale. I know it's hard to believe when we've got such huge projects as Whiteley just outside of Glasgow. We've got Viking up in Shetland, which is another, these are some of the largest onshore wind projects in the world. But compared to offshore wind, they are not the scale that's going to deliver the kind of scale up that we require to do industrial production of green hydrogen. Onshore wind, gives us a very good opportunity to do pilot projects of reasonable scale, because we have a number of projects that are over 100 megawatts. But if we want to do 100 megawatt electrolyzer projects, we need about 250 megawatts of wind. We don't have that many onshore wind projects of that scale. You know, as I say, we've got the Isle of Lewis, we've got Shetland, and we've got projects that are yet to be built in Scotland, but they're not all readily, what would I say, available, because the companies involved are looking to produce electricity first and foremost, and there is not a demand in Scotland or the UK at the moment that could actually satisfy that kind of scale. You know, if we produced a 100 megawatt electrolyzer project, it could probably drive every hydrogen vehicle that we've got in the UK for some time to come and still have plenty left over. So we need the supply and we need the demand to arise at exactly the same time, and we need to actually maneuver the market to do that. So support from UK government is very important. So we mentioned the contract, carbon contract for difference. That is the kind of support mechanism that would drive market development, and we need that in conjunction with the scale up. And at the minute, we just don't have the demand, whereas what's happening just now is that we are looking to Europe, because the European demand is climbing quite dramatically, particularly in countries like Germany. And we see the initial opportunity as perhaps an export one, where we will do it at scale and export it to Germany. But we have the time. The call was for the next 5 years. If UK government decide to support this industry, support the production of green hydrogen, we could see demand climb very rapidly in Scotland and the UK.
Okay, we've got another question just come in. Will the P2X subgroup be only focused on hydrogen production, or will the other energy vectors be considered, as you mentioned?
Yeah, that's why we've called it Part-X, because we're open to turning electricity from offshore wind into anything that can find a way to market. Now that includes, Part-X also includes energy storage, so battery storage, heat storage, whatever is commercially viable in the future, we want to look at as part of that Power-to-X subgroup, so that we're not missing a trick, and we want to be at the leading edge of turning offshore wind electricity into commodities or other products which can find a way into the energy systems approach and contribute to combating climate change and decarbonisation. That's what we're all about.
Okay, we don't have any more questions now.
In that case, Paul, I'll jump in and just say thank you for a very good overview of the sort of the green chemical industry. I found it fascinating, even though I've heard you talk before. It was really interesting to hear it again. So I can only give you some virtual applause, but thank you for taking the time this afternoon to speak to us all.
Well, thanks, Bill. Thanks for having me. And Jennifer, thank you. Okay, thanks to everyone for tuning in. And if you do have any questions, I shared my email on our website, offshorewindscotland.org.uk. Happy to take any further questions that you might think of at a later stage.